This standard is about applications of quadratic equations. Quadratic equations are important because they can be used to describe something that you throw, and I think you can imagine that throwing things and wanting to know where they land and how high they go has been a problem that's been important for a long time. And if you throw something on Earth, the way that the Earth's gravity and the object interact, you get an equation that always looks sort of like this one, negative 16t squared plus some number times t plus another number all by itself. This negative 16t squared, that always comes up on Earth because of the way Earth's gravity is. The 10t, 10 represents the object's velocity when you first threw it, and 5 represents how far the object was off the ground when it was thrown. So let's look at solving one of these equations. Sally tossed a beanbag at a target placed on the ground. The path of the beanbag can be represented by the equation h of t, and this is function notation. Remember from earlier in the year, the height as a function of time. So h of t equals negative 16t squared, and the negative 16 comes about because of the way gravity works on Earth, plus 10t. 10 is the velocity the beanbag was thrown at, so it was thrown at 10 feet per second. And 5 is the height off the ground when the beanbag was thrown, so 5 feet. How long will it take for the beanbag to reach the target? So it reaches the target when the height is 0, because the ground is a height of 0. So that means I can replace the height h with 0, and that's going to equal negative 16t squared plus 10t plus 5. So this is a quadratic equation. And I know a bunch of different ways to solve these. The way I'm going to go with is the quadratic formula, because I don't think I can factor negative 16t squared plus 10t plus 5. So for the quadratic formula, a is going to equal negative 16, b equals 10, and c equals 5. So the time, t instead of x, is going to equal negative b plus or minus radical b squared minus 4ac all over 2a. So I'll start replacing some numbers here. So the time when it hits the ground is going to be negative 10 plus or minus radical 10 squared, which is 100, minus 4 times negative 16 times 5 all over 2 times negative 16. So that equals negative 10 plus or minus radical 100. 4 times 16 times 5 is 320, and there's two negatives there, so I'm going to add it, all over negative 32. So we'll keep on simplifying. This is negative 10 plus or minus the square root of 420 over negative 32. The square root of 420 is about 20.5. So this is negative 10 plus or minus 20.5 over negative 32. So the time's going to have two possible answers. Either the time is negative 10 plus 20.5 over negative 32, or negative 10 minus 20.5 over negative 32. This first one's going to turn out negative because the number on top is positive divided by a negative, so that's no good. But here I have negative 30.5 divided by negative 32, which is about 0.95 seconds. So that means it'll take about 0.95 seconds, or a little less than 1 second, for Sally's beanbag to land on the target. Now we're going to think about John and his rubber ducky. So John is standing on a bridge, and he drops his rubber ducky into the stream below. The equation of the ducky can be given by the height as a function of time is negative 16t squared plus 48. This equation is a little different from the last one. There's no number multiplied by t. That's because its initial velocity was 0. John didn't throw the rubber ducky, he just held it out and dropped it. So this equation looks a little bit different, and it's a little bit easier to solve. We're going to find out how long it takes the ducky to fall in the stream. So when it's in the stream, the height is 0. we want to know when that equals negative 16t squared plus 48. So this equation, because there's no t term, you don't have to use the quadratic formula. I'm just going to be able to take the square root of each side if I get t squared by itself. So I'm going to add 16t squared to each side. 16t squared equals 48. And then I'm going to divide each side by 16. So t squared equals 3. Take the square root of each side. And the amount of time it's going to take for the ducky to fall in the stream is going to be the square root of 3, which is about 1.7 seconds. I also have another question I'd like to ask here. I'd like to know how far the ducky will have traveled after 1 second. So what I'm asking there is what's the height at a time of 1. So the height at 1 second is going to equal negative 16 times 1 second squared plus 48, or negative 16 plus 48, which is 32 feet. Now we're going to think about a tennis ball machine. I think you've probably seen these before. They throw tennis balls at a player so they can practice their return shots. And the height of the tennis ball off the ground is given by this equation. H of t equals negative 16t squared plus 32t plus 4. So what's the maximum height that the tennis ball reaches? So let's draw a little picture that kind of shows what's going on here. As time goes on, let's see, it's at 4 feet when it starts, because that's how far the machine is off the ground. It goes up in the air, and then it's going to come down and land on the ground. So this is time, and this is height. So the maximum height the tennis ball reaches, that's like finding the vertex of the parabola. So first I'm going to find, we've been calling it the x-coordinate, but it's the t-coordinate, because that's what I've got down here. So the time when it reaches its maximum height is going to be negative b over 2a. b is 32, so that's negative 32 over 2 times negative 16, which is negative 32 over negative 32, or 1 second. In order to find the height at 1 second, I'm going to take 1 and I'm going to plug it into this equation here. So h of 1 equals negative 16 times 1 squared plus 32 times 1 plus 4, which equals negative 16 plus 32 plus 4, which is 16 plus 4, or 20 feet. So after 1 second, the ball is going to be 20 feet off the ground, and that's going to be the maximum height that it reaches.